research in industry, that's what machine learning is. Now, I told you I work for I consult for a number of cybersecurity institutes on machine learning. How does security relate to machine learning? Any guesses?
Take breaches in security that happened and use that to try to catch it as it's happening in real time in the future.
Yeah, that's a very good example. Detect intrusions, detect malware, detect malicious software using machine learning. Now, there's another side of machine learning that is not as commercially focused on as the other side, finding bugs and finding vulnerabilities and finding intrusions. And that side is adversarial machine learning, finding vulnerabilities in machine learning itself, finding ways to manipulate machine learning models. So the tutorial that I'm going to give you now in the next half hour, hopefully, is the first lecture I prepared for a course on adversarial machine learning that I'm going to put on probably my own website. You can check it out later if you want. And what we're going to talk about today is an introduction to ways that machine learning models can be manipulated by adversaries. How's it different from robustness of machine learning? You've probably heard the term robustness in your literature survey or your own work, right? The major difference when you talk about adversarial machine learning is in the fact that there's an adversary who intentionally aims to manipulate your model. Robustness doesn't necessarily talk about an adversarial intention. Robustness can correspond to safety. You want to make sure that under all circumstances, your model performs as expected. But under adversarial or hostile conditions, we are in the realm of adversarial machine learning. So does anyone know an example of adversarial attacks in machine learning?
Have examples of using intentionally adding noise to images?
Precisely. So that's known as adversarial examples. I've already given a talk to the previous series of these seminars on adversarial examples. So let's say we have an image classifier, and this classifier is essentially trained to classify different types of animals from images. If we give it an image of a panda, what it's going to do is to, hey, tell us between the classes that it's trained on, this one corresponds to a panda. But if we add some noise to it, something that looks like random noise, but it's actually strategically derived or crafted for this particular input, the output of the classifier is going to be different. But you notice that with our naked, naturally evolved human eye, that one still looks like a panda, right? That's the beauty of adversarial examples. You don't have to change much in the content of the image so that it would look different to a human observer, but just modify it with tiny perturbations so that a classifier, for example, a deep learning classifier, a convolutional neural network classifier, misclassifies it. This is known as adversarial examples. If you want to learn more about adversarial examples, I gave a more in-depth talk, I think it was last November, and it's on my website. You can check it out too. Now, the question is, why should we care about pandas? Our Chinese friends, why should we care about pandas?
Because they're cute.
Of course. But is that an economic reason? That too. But in the AI realm, why should we care about a panda being misrecognized or misclassified?
Isn't a panda like in Python a data structure?
Pandas is a library too, yeah. But yeah, that doesn't really relate to this particular context. So
It's like black and white without the grayscale property.
that's an amazing observation. That's an amazing observation, and I had not thought about it before. Well, if anyone comes up with a great idea during my talk, they're gonna receive a fist bump. Well done. But no, that's not the reason I was talking about. It's not just applicable to pandas. Let's say you have an autonomous vehicle. You have a Tesla on autopilot who's trying to look at street signs and try to classify them under different classes of street signs and modify its action based on the image received or image observed from the street sign. What happens if we add some adversarial perturbation or adversarial noise to the image received, to the image of a stop sign? What's going to happen?
Car's not going to stop.
Car's going to do something else. Like this. So we can actually add some adversarial noise to an actual stop sign or the image perceived by the autonomous vehicle from a stop sign and make it do weird things. Yeah,
Question. What do you mean by noise?
that's a very good question. Modifications to pixel values
Okay.
in this context.
Okay.
But if you want to learn more, Bill, is that a breach of privacy or the Slack messages?
It's all right. It's the KDD.
Okay. So, in the context of image recognition, it's just pixel values. Okay. But adversarial examples apply to text classifiers. They apply to speech recognition. They apply to intrusion detection systems. They apply to antivirus and anti-malware systems. They apply to literally everything that involves some sort of machine learning model. But they're just an example of adversarial machine learning. Why should we care about adversarial machine learning? So I attended two of the better known cybersecurity conferences, non-academic cybersecurity conferences in the US and in the world. Black Hat and DEF CON. Have you heard of Black Hat and DEF CON? Okay, so this year, the hype word in the cybersecurity world is AI. Almost every major and minor company in the cybersecurity domain is leveraging some sort of AI and machine learning, or at least claiming to use some sort of AI and machine learning in their products. Cylance is very heavily involved in using AI in their antivirus and other types of technologies. And you can see these are some of the startups that are heavily based on AI. Endgame is a very interesting company. They are actually doing some adversarial AI research themselves, but every other company that you see here is actually producing vulnerable cybersecurity problems based on ML. Why doesn't anyone care about it? Why do they still keep using vulnerable AI in their systems?
Because it's better than what they had before.
No. So I actually had a verbal fight, a very heated argument with the people at Data Science and Microsoft about what they presented as their solution, as their AI-enabled solution for Windows malware detection. And their Windows malware detection system is at best able to prevent 65% of intentionally perturbed malware. Before, when they were using signatures, it was working with an accuracy of around 99%. Why do they insist on using AI? Why do they insist on using machine learning models?
Sounds cool.
One reason.
So that maybe if that's out there, then there's going to be a lot of breaches to go through in that other 35%, and then they have more to try to figure out and learn from.
Yeah, so suicide mission for the betterment of the future, right? What else? Security by obscurity. They actually think that the number of people who know about adversarial machine learning is far less than the number of people who know about machine learning, and the number of people who know about machine learning is like a fraction of 1/10,000th of the population of the Earth. And they think that no one knows enough about adversarial machine learning to exploit their models. The same thought went into the design of the internet. The same thought went into the design of the web, the email protocol, the DNS protocol that's being attacked almost on a daily basis, and the IoT and everything else. So a historic mistake is being repeated here. Where else does it matter? AI is being heavily implemented in critical infrastructure. So I gave a talk on the security of airborne systems, particularly drones, UAVs, unmanned aerial vehicles. And it was really interesting for me to find out that a few months ago, people have started implementing automated ATC agents. Does anyone know what ATC stands for?
Air traffic control.
Air traffic control systems that are still vulnerable, but they don't know about. The same thing is being applied for optimization and control of smart grids or power grids. Are you scared yet?
Well, so this premise doesn't work even if it is obscure to humans, right? Because you don't need a lot of people, a lot of attackers to understand your machine learning algorithm to be able to counteract it. You just need a few that are able to deploy agents that can exploit.
That's very true. This is not in my slides, but my general take on this is the field of AI, applied AI and applied machine learning is very young. There are no regulations and there are no standards for checking the resiliency and robustness of AI models in deployed environments. Some people still apply software resiliency and software reliability tests to AI models. And that's how they get it up to date and is not in the same pace as the developments of the machine learning field. That's why a lot of these models are being deployed in critical infrastructure and security products, and believe it or not, in government organizations like the DHS or the Justice Department. Okay, any questions so far?
Can you shed some light on why this is an endemic problem in cybersecurity? Because the fact that security through obscurity doesn't work seems to be a fundamental tenet, or should be.
There are three kinds of people employed by the cybersecurity firm of the run-of-the-mill cybersecurity firm. The first type is a cybersecurity expert with a lot of experience and background in cybersecurity. The second type is a data science expert with quite literally no background in cybersecurity. And the third kind is a manager who wants to make a product and make money. So there are very few data scientists with cybersecurity background. When I say very few, I actually mean very few. My current estimate is there are less than 500 people with the shared kind of background between cybersecurity and data science. There are cybersecurity experts who started to learn data science and machine learning, and there are data scientists who started to learn the basics of cybersecurity, but there are very few people who have a very good understanding of both domains. And those two types of experts are pressured by their manager to release a beta or a production-ready system. And no one is capable of automating the testing process, the adversarial testing process. One of the projects that I'm involved in right now, and I'm raising funds for it, is an open source automated penetration testing model or framework for deep learning. And it's gaining a lot of attention, but a lot of companies don't want it to go through. Silence, for example, is one of the big opponents of this project being funded through OWASP, the Open Web Application Security Project, because they know when it comes out, a lot of their models will be obsolete and their market share may fall. This is a very dangerous environment, but as machine learning researchers and probably machine learning engineers of the future, you need to be aware of the dangers. You need to tell your manager, hey, there is this fundamental flaw in our deep learning models. I can give you a deep learning model that does the thing you want it to do, but it is going to be vulnerable to sophisticated attacks, the same way that a human learner is vulnerable to manipulation. Yeah?
So you're saying people are using machine learning not the right way. They're using it in the...
I'm saying we don't know what the right way is.
No, I'm saying like...
We don't know how to secure machine learning models. Let me keep going.
Yeah.
So, let's say there's an attacker who wants to attack a machine learning model. What could they be after? For those of you who have taken a security course or have worked on cybersecurity, you're very familiar with the CIA triangle. Well, there is a dot circling that triangle over there. So, you know the confidentiality, availability, and integrity aspects of cybersecurity. Confidentiality in machine learning refers to making sure that the model itself is not prone to leakage. Your competitors are not able to find out what the model that you're using in your commercial product is. Do we have that in the current AI environment, in the current ML system? No, we don't. It's actually pretty easy to estimate a lot of the commercial deep learning and non-deep learning models that are out there. All you have to do is to send in queries and see what the response is, create an offline data set of query and response, and then model it yourself. This is the simplest case. Some people have used differential privacy schemes and other types of schemes like randomization and all that to make this harder. But last year, Nicola Paterno and Ian Goodfellow, two of the very well-known names in the adversarial ML community, came up with a very interesting technique based on generative adversarial networks that kind of circumvents all of that defensive approach with randomization. The second problem is the privacy of the training data. Let's say that you have a model that's trained to diagnose patients based on an X-ray image or a CT scan or an MRI image. What if there is a way for the attacker to reverse the model and find particular information about a particular patient whose data was used in the training of that model? That also is possible, and that also is a very hard thing to defend against. What are the other problems? Integrity and availability. Integrity of predictions. Prediction in machine learning essentially refers to the outcome of the model. So we learn something, for example, in a supervised machine learning environment, we learn a function that maps between an image input to a class output, and then we apply to unseen data. That's a model. What if we can give it an input that produces an incorrect output? This doesn't only apply to supervised learning models. This can apply to unsupervised models. This can apply to dimensionality reduction. And one thing that Arsalan and I, Professor Monir and I showed for the first time, this can apply to reinforcement learning and deep reinforcement learning. What else? Availability of the system. So some of you have heard about denial of service. Is there a way to attack machine learning models so that it wouldn't work anymore? There is. Is there a way to defend against all this? There are ideas, there are proposals, but nothing concrete as of yet. I have to check again. Are you scared yet? Cool. We'll get there. So, what are the adversarial capabilities? What is the adversary? What is the attacker capable of? We can come up with different types of models, or threat models, or attack models. One of them is based on when the attack happened. After the training is done, and now you have a model that's trained and is deployed to the world for some certain application. You've all seen examples of training time attacks. Can you give me an example? You all use Google, right? You're all believers in Google, hopefully. Have you seen the tampered or manipulated autocomplete results from a Google search? Like, if you go to Google, or a few years ago, if you went to Google and search for, I don't know, why is an academic or why is a university professor, and then it came up with very sarcastic results. Why is a university professor always poor? Or something like that. These were intentionally manipulated models during training or online training. Can you think of another example of training time attacks?
Bayesian poisoning and spam.
Definitely, yes. So we'll go into that later, hopefully if you have time. Let's say you have an autonomous vehicle who's learning based on some sort of learning algorithm. My personal bias is towards deep reinforcement learning, to navigate in an environment. At training time, can you be the bad influence and teach it to hit every 4-year-old that it sees? Can you? Yes. Yes, you can. Now, inference time or test time attacks happen when the model is done training. Of course, there are models that do online learning, so at the same time that they produce outputs, they do inference, they do training as well. But many of the models deployed right now are trained at a certain period and then deployed in the environment just for the testing purposes. Yep.
Wasn't Tesla working on something similar to this, an autonomous car?
Yeah.
Whereas when it gets closer to a person, it just completely stops.
Yeah.
I mean, I think they have done it too, and they have done.
There are a lot of companies working on autonomous navigation in driverless cars, and almost all of their approaches is vulnerable. And very few people are willing to admit it, because then the stock of their employer is going to crash and they're going to lose their pension.
It has happened. There are videos.
Well, the accidents that have happened are actually not adversarial attacks as far as I know.
Okay.
But it is possible to mount or launch adversarial attacks against those systems.
But are you talking about accidents or are you talking about adversarial attacks that people demonstrated?
Not that. I'm talking about the accidents.
Yes, so there have been accidents. So Uber's self-driving car actually killed a person in Arizona. I think it was in Phoenix, if I'm not mistaken, a few months ago. Before that, there was a Tesla autopilot accident somewhere in Australia, if I'm not mistaken. And there have been other instances of accidents. Like 3 years ago, it was a huge headline in the papers when the Google self-driving car had an accident with a school bus or just a metropolitan bus somewhere in Palo Alto. But these are accidents. These aren't adversarial. When you intentionally make the machine learning model behind those autonomous navigators to collide with another person or another vehicle, that's considered an attack. And there are no news of that yet. There are people working on this sort of attacks against military drones, but it's not open source. When it comes to inference time attacks, there are two types of attacks. white box attacks and black box attacks. White box attacks occur or can happen when the adversary has complete knowledge of the model that is trying to attack. What do we mean by complete knowledge? If it's a neural network, the attacker knows all the weights and all the hyperparameters of that neural network. If it's a linear regression or multivariate regression model, it knows all the coefficients. The attacker knows all the coefficients. So the attacker knows the model, has a copy of the model, and then it tries to find an input that will cause the model to miscalculate or come up with an incorrect output. The black box attack, on the other hand, is when the attacker doesn't have any or much information about the targeted model. Let's say you want to target Gmail spam classifier. You don't know what the model parameters are, right? But as is proven to us on a daily basis, there are ways of getting your spam through Google's spam classifier. These are black box attacks. Any questions so far?
What do you call the kind of attack where you know the model parameter values, but you don't know the updating algorithm?
Well, that's a training time attack if you're talking about the updating algorithm, right?
Sure.
For training time attacks, you can still have black box and white box, and then in black box, there are certain attacks that you have some knowledge of the model, but not full knowledge of the model. And then again, if you don't know the updating algorithm, it doesn't really matter. Because
Do they call that gray box, or is there an actual?
Yes, some people call it gray box, but the old school people like myself still stick with black box attacks. For this particular example that you said, when the updating model is not available, it's not necessarily gray box. Nicola Paperno in that paper that you showed me in the magazine starts defining gray box attacks, but that doesn't apply to this particular example because there is transferability between different types of updating algorithms in the same model. Now, let's talk about integrity attacks, attacks on the integrity of the model. One type is evasion. So, the objective of the evasion attack is for malicious objects to be deliberately transformed to evade detection. Let's say you have a spam classifier or malware classifier. You want to evade the classification of your malware or your spam email as a spam and malware, right? There's a different type of attack, and it's called poisoning or data poisoning. Data poisoning usually occurs at training time. And what does that mean? It means that the adversary introduces malicious modifications to data used for training. Like, if you have samples of spam emails with labels that says these are spam, then the adversary includes emails that are spam, but are very similar to those samples, but are labeled not spam or safe. Does anyone know what the technical opposite of spam is? Any guesses? It's ham. So spam, ham. We'll see that later on. So if you can manipulate the training data set, you can essentially mount or implement a data poisoning. The crucial distinction between these classes of attacks is evasion is an attack on the learned model, or the actual classifier, but poisoning is an attack on the algorithm, on the learning algorithm, and it usually happens at training time. Adversarial examples, that Panda example that I showed you, is usually considered an evasion attack. Well, this slide is slightly irrelevant here. So this is the first set of lecture slides that I created for my course on adversarial ML. And I'm going to talk about evasion attacks, poisoning attacks, and AML and deep neural networks and reinforcement learning and all that. It's 5:20. Do you guys want to hear more about evasion attacks for the next 10 minutes? of your enthusiast. Okay. So, before I start this lecture, there is a project, an open source project based on TensorFlow, PyTorch, Keras, or any other major machine learning library that you use for generating adversarial examples. This library is called CleverHands, and well, a little bit of marketing and bragging. I'm one of the top 10 developers of CleverHands, so if you find any alternatives, try CleverHands first and then go to the alternatives. You can play around with adversarial examples against deep learning classifiers and see how easy it is, how simple it is to create adversarial examples or evasion attacks against classifiers. So, we know about the classification task. We're going to talk about evasion attacks. We know about learning a classifier or training a classifier. The objective is to come up with some sort of surface or manifold that makes a distinction or defines a boundary between different classes of data, right? Often, in many applications, what classifiers are tasked with is to tell apart good from bad, especially in the cybersecurity. When you get an email or a notification from your bank telling you, hey, there's been this transaction and it looks abnormal to us. Are you sure it was you that did or well actually implemented this transaction? This is an anomaly detector or an anomaly classifier at work. Another example is spam versus non-spam. Another example is intrusion detection. Another example is malware and non-malware in your antivirus system. So the adversary would want to make these classifiers, good or bad, to misclassify something malicious as something that's benign, right? This is the premise of an evasion attack. Let's look at an example. So if you get an email with this subject line, cheap mortgage now, it's very, very, very straightforward for even a linear classifier, a linear regression model, to learn a classifier that classifies the subject line as a subject line of a spam, right? Because it has cheap and mortgage, two spam keywords. So how can we evade this type of classifier? Let's change cheap mortgage to Joy, Oregon. Just two very benign, non-threatening, non-spam related words, right? That's one way to evade a spam classifier. Now, if you want to model an invasion attack, the idea here is the attacker is producing or giving rise to a feature vector, vector corresponding to the malicious object that the attacker wants to get through the classifier's information. Now, what the attacker wants to do is to modify that vector such that the malicious nature of it is preserved, but the classifier misclassifies it as a benign vector or a benign object, right? Very, very scared looks. This math here is really simple. So the objective for evasion is to minimize the cost of perturbing or modifying the original malicious vector of features. So let's say that whenever the attacker changes a certain feature by a certain amount, it's incurring a cost to the attacker, right? The attacker wants to minimize the cost such that the resulting modified vector is classified as benign. This is all the math tells you. And in many cases, the attacker wants to keep the modification small. Why? let's say you are a spammer and you want to get your spam email through. You're advertising to Viagra or I don't know, some other more respectable medicine. And you want the message to go through. You're selling your medicine, right? If you perturb it too much, the message may be so obfuscated that the potential customer doesn't really get what's going on. Okay, so there are different models that approach this problem. I'll upload these lecture slides later in the Slack channel and you can look into them.
Isn't there a inverse form of this where if you induce too many false positives, it basically renders the classifier useless? So if you actually take legitimate messages and mix them in with spam words so that I start losing useful email, then it makes me turn my filter off.
So in the old days, that would constitute a denial of service attack. In the present day, considering the fact that, for example, Gmail's spam classifier is automatically retraining itself on new data, this is called, or this falls under the class of poison. And this is actually a very, very huge problem. There is a group at Google who's been working on this problem for the past 4 years. Ian Goodfellow is actually the head of that group now. They're working on making sure that the classifiers and machine learning models deployed by Google on the front end, the customer side, are working fine. But there are no concrete solutions there. Microsoft, based on the conversation, the very heated conversation I had with them, uses a human in the loop. But considering the bandwidth and the amount of information that goes through every second, they actually need to employ as many people in that manual verification as there are in Africa. That's an actual figure. This isn't an exaggeration. Okay. So this is going to, these are a little too detailed for a 525 lecture. So let's look at this example here. This is a spam email. And we have a linear classifier. We have a model based on linear regression that's trained to essentially classify spams based on the presence and frequency of certain keywords. Right? See how easy it is to convert spam to ham. Are you ready to become more active? Are you happy to become more active? Happy is a very, very prevalent word in typical emails, right? Product is often related to spam in certain data sets. I've actually seen the data set that this example comes from, and I use it as a practical example in the course that I'm developing. So product, this was actually very, very highly related to spam, but merchandises is not. Losing weight, you can keep weight here because weight can be both related to spam and not. There's a relevancy score, or spam-related score that you can give to every keyword. Clear?
So it doesn't have to do, I thought it was.
Oh yeah,
misspelled.
there's a spelling problem there too, and you still see that in Gmail classifier. So if you go to your spam folder, you see that the older spams that you receive have actually intentional misspelling. Some of this still goes through Gmail's spam classifier, and you're right, clearance is misspelled here. That's how they evade the classification of these two as spam-related keywords or presence of spam-related keywords, and then cheapest is converted to deepest. Does that have a meaning? No, but when you read the sentence as a human being, you probably understand that, hey, this is talking about cheapest. This right? This is how easy it is to mount an evasion attack against span classifiers. Now, the rest are a little too technical. Oh, dimensionality reduction. When you do dimensionality reduction on your data to train a model, before training a model, what you're actually doing is you're getting rid of a lot of salient information that may be useful in proper classification. So when you reduce the dimensions of, I don't know, a video before training an, I don't know, adversarial action recognition, there are systems deployed in banks and certain federal government buildings that look at the CCTV feed and try to recognize certain actions as precursors or indicators of attack, right? They most certainly use dimensionality reduction, and that dimensionality reduction makes the task of crafting evading inputs a lot easier. So I used to live in a city in the UK called Birmingham. Birmingham had the largest number of CCTV cameras deployed in the city area. And all of those were connected to a facial recognition data set and model. It was shown, I think about 5 or 6 months ago, that the smallest amount of makeup or the smallest amount of change in your facial characteristics, like if you have beard, you just shave it off. If your eyebrows are connected, you just do whatever it is that some people do to make them distinct. The smallest amount of changes in your facial features is going to make that model misrecognize or misclassify. And this is the equivalent of DoD and the UK's MOD, Ministry of Defense. That was an MOD certified biometric model. And this is how easy it is to fool those models. Another concern is, does security by obscurity work? Does keeping the parameters of your model to yourself and confidential work as a mitigation against these sort of attacks? Most certainly not. No, it doesn't. Because the model can be approximated or inferred by a motivated adversary. And the rest are a little too technical. I'm going to call it for now because it's 5:35. Thank you very much for attending the talk and showing some interest.